Welcome, and thank you for your interest in my poster. I will present some modeling work that we have done considering top-down gating signals for cognitive control and learning. In order to perform on a wide variety of tasks, the human mind should be able to separate neural representations for different task sets, this to avoid interference. However, one can imagine that during learning, it might also be beneficial to share neural representations between task sets. This would allow for generalization between tasks that share certain characteristics. When we look at artificial neural networks, different task sets are often implemented by a top-down gating signal. Importantly, there is quite some variability in how such gating signals are implemented. We construct a basic network in which we evaluate different gating signals indicated here by the red line. Two dimensions of gating were explored. First, we explored whether this gating input was best processed in an additive way, so just added to the network like any other input, or in a multiplicative way. A multiplicative signal would allow to basically turn off hidden neurons by multiplying their activation by 0. A second dimension that was explored was whether it is necessary that these gating weights are able to learn, so whether they are adaptive. Previous work from Massa and colleagues has illustrated that just sending random gating signals was sufficient to allow a network to learn and perform on a wide variety of tasks. So crossing these two dimensions led to 4 different types of gating signals that we evaluated. We performed an extensive test of the network performance. We tested different input types, binary, continuous, and images, and for each type of input, we defined several task sets which had varying overlap in the amount of input-output mappings. For example, for the Stroop task, in which stimuli were coded as binary input arrays, we defined 5 task sets A, B, C, D, and E, for which overlap is presented in this table. 3 task sets, A, B, and C, were orthogonal to each other, so they didn't share any mappings. Task set D shared 1/3 of the input-output mappings with each of the previous tasks, and task set E actually used the same input-output mappings as A, but was implemented by a different neuron in the task set layer of the network. We evaluated different learning rates and different numbers of hidden neurons or layers. For each simulation, all task sets were trained 3 times in a blocked fashion, after which weights were frozen and the network was tested again on each context with novel stimuli. We observed that for all simulations, accuracy was significantly better for the adaptive multiplicative gating model presented by the blue line. This was the case for both the training and test stage. Moreover, we saw that the model was able to generalize between contexts that showed an overlap in input-output mappings. For example, in this case of a Stroop task, performance for task set A, D, and E was better than for task set B and C. This is because, as you can see in this table, task set B and C shared in total less overlap with other task sets. We also evaluated whether neural representations in the hidden layer reflected actual overlap in input-output mappings between contexts. To do this, we defined for each simulation the true overlap between input-output mappings, like in this table of the Stroop task. Then we computed a representational dissimilarity matrix for activation in the hidden layer across all task sets. This true similarity was then correlated with the representational dissimilarity in the network. Correlations of -1 would thus indicate that the model was able to capture the true overlap between task sets. As you can see, correlation was lowest for the adaptive multiplicative gating model. Moreover, when multiple hidden layers were used, we observed that although the gating signal was only sent to the first hidden layer, representational overlap between task sets was more clear in the second hidden layer than in the first hidden layer. Therefore, we conclude that for continual learning of multiple task sets, an adaptive multiplicative gating signal is most optimal. This gating signal allows to mirror the actual overlap between task sets and hidden layer activation. Therefore, the network is able to both avoid interference as well as generalize knowledge from different task sets. For more information, please contact me on this email address.